Well, welcome back to the second plenary session this morning. It's both an honor and a pleasure for me to introduce both of our plenary speakers. Our first speaker is Dr. Tayo Akinwande. He's a program manager for Microsystems Technology Office at DARPA, and he's also a professor of electrical engineering and computer science at MIT. Tayo received his PhD in 1986 from Stanford, and then he's at MIT. He's in the Microsystems Technology Laboratory, where his research focuses on microstructures and nanostructures, MEMS and NEMS, for sensors, actuators, vacuum nanoelectronics, large area electronics, particular emphasis on smart sensors and actuators, intelligent displays, and devices based on charged particle beams. Prior to that, he was actually at Honeywell, working on gallium arsenide FET technology for high-speed, low-power signal processing applications. And he was a member of the Honeywell Silicon Microstructures Group. We conducted research on pressure sensors, accelerometers, thin film field emission, and display adapters, or display devices, I should say. His interests at DARPA include emerging micro and nano electromechanical systems, large area microsystems, and electronic actuator devices based on charged particle beams. He's also a manager of the tip-based nanofabrication program at this. And there are actually two groups at Illinois that are participants in that program. He's received numerous awards, including the 1996 NSF Career Award, the SWEET Award from which is Honeywell's highest technical award. He served several technical conference committees, organizing committees, including the Device Research Conference, IEDM, International Display Research Conference, and International Vacuum Microelectronics Conferences. He's also chair of the IEEE Electron Devices Society Nanotechnology Committee, and he's a fellow of the IEEE. Please join me in welcoming Dr. Tayo Akinwande.
I would like to thank the organizing committee for inviting me here. And what I will try to do within this is give you a flavor for the activities at DARPA in what I call the nano area. And I'm not going to be giving you all the offices, but I'll focus on the Microsystems Technology Office which I work in. But also in the process, try to describe how DARPA works so that you know how to fit your programs or your ideas into how to get programs started. Just to give you a flavor for, there are 6 offices, and 2 of them are what I call technology offices, MTO, which I belong to, and Defense Sciences Office. And these are the types of technology. For example, a lot of the biological science that was talked about this morning would naturally reside in the DSO office. But it's also the one that does basic mathematics and does a lot of material science. MTO tends to focus on microsystems and nanosystems, basically to make things more. But you have systems offices and technology from DSO and MTO feed into information innovation office, system technology office, and technical technology offices. And one thing that I would say that's also it's important to note about DARPA is that its mission is to prevent technological surprise. And so if that's the case, in the process you develop technology, but its real mission is to prevent surprises and also to create surprises. And so it's that dual mission, and we look for big gains in anything that we do. We don't want to do 10% gains, but we like to see a factor of 10,000 gains in performance. But it never really works unless you have great program managers. So the vision of that is really driven by the program manager's economy. So the vision of the program manager, you have spent 4 to 6 years working in that project, and you create programs, and you have a limited time. Everybody rotates out. So you do whatever you can in that short time. So your way of working with DARPA is to walk through the program managers that come in. And I'll put a pitch in there, send program managers from Illinois, please. And so the programs that tend to be capabilities, it's a mission focused, and everything starts and dies. There's no question about that. If a program has been there for too long, it's one of the things that is candidate for being eliminated. You may restart in some other form, but things start and go away. And we tend to use a lot of diverse performance. We don't only use academia, but you can see it's an interplay between government labs, agencies, which tend to tell us what's needed a lot of times. And you have industry, which tends to tell us what can be done now. And academia will provide ideas into the future. And it's that mix that you try to bring together in your programs to move things ahead. And it's very multidisciplinary. For the last few years, 5 years ago, it was difficult to get single investigator programs going. But now, it's possible to have single investigator programs within a larger program. So, with that, and so I kind of spoke about this, most of our programs, and it's important that I put it's project-centric, empowered by ideas and passion of the program manager, and usually we create teams that do this, but it's also possible to do single investigator program. And one further thing is that we are driven by quantitative milestones. So there's always a goal of where we want to get to. So with that, let me get into my office, which is MTO. We tend to do things in the area of devices, integration of devices, power, and architectures that drive these devices, applications, and we do some basic science. The reason I talked about this is how does Nano fit into all this? There's a lot of Nano, but they have to deliver on the terms of how do we improve performance, size, weight, and power, and enable adaptability. What do I mean by enable adaptability? Well, in classic case, take the microprocessor. It's easy to reprogram it, or maybe the FPGA. It's easy to reprogram it. That's adaptability. At the same time, we would like to have all the performance you can get. So I would like to have the performance of the ASIC and the application-specific integrated circuit, while being able to have the flexibility of the microprocessor, if I can get it. So we focus on trying to systems, but at the micro and nano scale. It's driven by what systems can we build, but do it at the micro and nano scale. So to give an example of a little bit of that, these two axes kind of tell the kind of thinking that goes into how most programs are approved. We want to get into how small can we make things. In this case, we use 1 over, these direction tells you things are smaller. So, and then performance, whether it's faster or more linear or higher power or low, higher power performance that you can get goes in that direction. So, and a good example is a chip scale atomic clock project that we did. Is to take an atomic clock that is a laboratory device, or make it such that it actually can fit on instruments that, or devices that can be used in the field. And that required a lot of new science, because one of the skepticism that was there was that, are you going to make this with all the scaling things down, the walls are much smaller, things, you're going to have a lot more surface, surface interaction, as in because your surface to volume ratio goes down. goes up significantly. But people came up with clever ideas to avoid wall collisions, and now we have chip-scale atomic clock. But if you've been conversant as to what the BAs are out there, we walk through the broad agency announcements. There is another follow-on program that is going on now with one of the program managers, Andrew Schell. And it's really to combine what we can do at the atomic level and sensors. And you know, what happens in that case, it takes a long time to get them started. So if you are putting them on for a missile, sending them off, how quickly can you navigate through that? But at the same time, you can combine them with your regular gyroscope that you make with silicon. So you're now trying to see how to combine devices. One that is based on the atomic and combine it with something that is based on the microsystem scale things and get a performance where you can get both of them. So if you check the BA world now, one of the programs that is going. Another case that you can look at is the power density that comes from microelectronics. Gallium nitride has taken over as one of the high power devices that we can build. But also you look at your microprocessor, we've been stuck at 3 gigahertz for how long? Maybe 10 years. And the real problem is heat management. So there are programs that we're doing now that are going to increase the power density by removing heat. And you know, Habib Cohen has a program that will look at how to increase the heat power density by removing heat from the system. I'll speak a little bit about this. Of course, the better thing is to be over here, where you have both performance and size down. And in that case, you're looking at processors that have essentially multi-core elements, but at the same time working in the sub-threshold regime, really low power. So I won't spend too much about this in the sense that you know the MTO trust, focus on devices, integration, power architectures, and then microsystem applications. You always have to have this microsystems application. So a lot of MTO's programs are nano-enabled. We use nano a lot in this, but they focus on how to get systems going. So our value is derived from harnessing the capabilities that comes out of emerging technologies, in this case nano, and use it to increase size, increase performance of SWOT. Well, nano tells you that you're going to be smaller, so it goes in the direction we want it to be. It also means sometimes just faster. It goes in the direction we want it to be. But at the same time, it comes with some challenges. How do we connect them together? It raises problems we would like to work on. In the sense, how do we interconnect them? And so emerging technologies such as nano play a strong part in MTO programs in general. So, but you know, let's think a little bit about it slightly differently, just away from just size reduction. What are the bulk properties, behaviors that we can get that are not possible with bulk properties? And some of these, which I'll touch on, which comes on is building nano columns that becomes photoluminescent, and silicon being an indirect bandgap semiconductor, but when you shrink its size down, you start getting interesting properties. That is not available at the block, but we would like to leverage because silicon becomes something that we can integrate, since our office is mostly about integration of technologies together. And you probably out there's a program called DACI that is on our website now that is looking at diverse integration of technologies. And you know, and you know, last week we heard about Intel working at 20 nanometer FinFET. Actually, they started at DARPA with I think it was either Fabian Peace when he was office director, or Zach Lemnos, who is now the Assistant Secretary of I think Assistant Secretary for Defense for EDM and I think either one of them started it. And it was called at that time the I think it's either called the FinFET or, the depleted body FETs. But they started a program that later became, more than 10 years later, what's doing is 22 nanometer. And the challenge at that time was that there were 250 nanometers. They said, can we build 25 nanometer FETs? And this came true. And this is a program of mine, in which case we're using the gaps between the dimensions. And again, it's trying to solve similar problems. The problem here is that you have leakage current in a lot of your devices. A lot of your, even at 22 nanometers or even 65 nanometers, leakage current is a major component of the power dissipated in your systems. And so the thinking was that, and we know that because we have a solid materials, in this case semiconductor, that, as long as you apply voltage somewhere, there'll be leakage current through. And can you avoid that leakage? So can we use a vacuum gap as, and then use nanomechanical relay, which I'll talk about. And this device switches, goes back and forth. It's going back to the old relay, which were the things that you used to build the first computers. And we can switch back and forth and connect them. So, but if I said that this was all easy, I will be telling myself that we will not be faithful to ourselves. One of the things that we've seen is that we've been able to put nanomaterials together. In this case, the jungle carbon nanotube array. I won't call it an array, it's just a mat. In this case, we put it together as vertical carbon nanotubes. Or, let's take a look at this. We've been able to put a cross tab together, but it's telling that this is not in the center. That's the first thing that tells you that, can you really place it well? Can you place this over and over at the same place? So you can see that the challenges that this brings to us, even though we can build this, we cannot build 1,000,001 of them and connect them together. And that's what we need for building systems. And that becomes interesting to our office, because we are trying to build systems at the nanoscale. Yes, we can build this, we can do the materials, we can do one-off devices, but we are not yet at the stage of building systems. So we need tools for control of processes at the nanoscale. We need scalable methods for materials creation and manipulation. And we need approaches that can provide high throughput and consistent repeatability. And so we would like to move from here to this point, where this is your regular microprocessor, where everything is highly structured. But this is what we have today. And we cannot do 1,000,001 of them. So that's a challenge we would like to take on. So now, I will try to give you an overview of the programs within NTO that have nano in them. You see, I'm not saying, okay, these are nano people. I'm saying these are people who utilize nano within their programs to solve specific problems. I have a TBM program with Joe and Bill King are members of. I have the NEMS and MEMS fundamentals program, which John Rogers is also a member of. The nanomechanical switches program. And Scott Rogers, remember the silicon nanowires I pointed to earlier on? He's the guy doing that. He's more of a lasers and optics person. And he's an interesting mix. Tim Bodrick is a surgeon, at the same time a computer scientist. And so he's been looking at dialysis like therapeutics. And actually he has a PhD that is out now on e-mobile nanosensors that is out there. And he also does the surface enhanced Raman spectroscopy in order to do standoff detection. Harvey Bancoe works on thermal management. These are the nanothermal interfaces. And Jeff Rogers does a lot of what I call the mesodynamical systems, which I'll talk about. And I'll talk a little bit also about, the SERA program, which is a graphene-based silicon, graphene-based transistor circuit technology. And Brian Holloway is a materials person within ESO, it's not MTO, but he's trying to take a different look at, and we reduce the temperature at which we deposit high-quality materials. Typically, you do it at 1,000, but can we reduce that temperature to 100 by playing some, well, I won't call them tricks, but leveraging some understanding, some new insights that we have into our materials as well. And Joe Mangano is doing the nanowriter. And remember, if you try to build an ASIC now, the mass cost is about $7–10 million. Who in the university will try to do that? But he's trying to come up with approaches in which you use multiple beam electron lithography to do that. So let me go into the nanowriter. The key question is mass costs are killing us. And if you have any mistake on that, you're going to even get crimped by how much it costs you. So electron beam lithography has always been there. But the problem was throughput. Optical gives you throughput. And we surprisingly were able to use 9193 nanometer to do a lot of that. And yet we are now at 22 nanometers. So it's unphysical. It's not supposed to happen. The first thing I was taught is that, okay, you cannot define anything better than the wavelength of light. But guess what? Brilliant people like you in the audience have worked on it and really driven down ability to either increase numerical aperture or work with resist, do all kinds of tricks like double patterning. Eventually we're there. But I'm not sure beyond 22 nanometers we will have something that we can work on. So with that, the idea is to do multiple electron beam columns, where we start with an electron gun, which is a broad source of electrons, come around through a condenser lens, bend it electrostatically, and then send it through a filter and demagnetize it, demagnify it, and then send it through a dynamic pattern generator lens. This breaks the electron beam into 1 million small electron beams. So it takes a single electron beam, breaks it into 1 million electron beams, and turn them on using a CMOS chip. That is, and then with a set of columns that electrostatic lenses that are created, we backed up with a CMOS column, and then turn that beam around, send them back. Now they're broken up into small beams. They're now going down, and they go into expose the wafer. So that's the way that using to increase throughput. And this has been demonstrated, which they've showed 45 nanometer lines and spaces. All of them exposed at the same time. So one beam writing all of this, it's, in this case, I think 256 beamlets writing at the same time. So, and this is now going to be driven down to 16, 13 nanometers approach. So, the program that I have there is the TBN, tip-space nanofabrication. So, the other one was looking from the top down. In this case, we're going to look bottom top. And in this case, think of the fact that we can build quantum dots. And what's the problem with them? Usually, yes, you can build 10 of them, maybe 20 of them, but there's always one that will have defects somewhere. We do things in which case we localize the reaction. First, we need to place things exactly where we want to have them. So you localize the reaction by using, in this case, tips to help you by either using an electric field or using, in this case, localized plasma, or using enhanced, concentrated photon beam to that tip. And then bring in your reactant gases, cause the reaction to occur, and there's a defect there, but you have to find out which one has defect. So you image with a tape again. Joe is one of our participants in this project. And then you go back after detecting to correct only the one and that has been and repaired it. And I'm happy to report that one of our colleagues here, Professor Bill King, is rating and stretching well done. He wrote paper, and in this case, using a lot of different tapes, in this case 5 tapes, which corresponds exactly to the number of letters you have in DAPA, so which works very well. First, did a first read, which tells you we have nothing on the surface, and then write, and then do a second read. In this case, he wrote horizontally, and then third thing, he did the vertical writes, and then read again. And you can see that you are a lot in that direction of achieving the ultimate program of write, scan, and repair. So another one, which has participation by UIUC, which is part of our TBL program, and this is Joe, part of the Zyvex team. And this is essentially, again, doing it at the atomic level, in which case, this is doing atomic precise, a very atomic precise tape, which is computer controlled. And first, you remove hydrogen atoms, and then come with silane, and then silane decomposes, or in this case, gaseous SiH2 radicals, and then deposits silicon, and then activate this cycle again with hydrogen, and then go back to write on that surface and taking off the hydrogen. And they've been able to build structures. But these would not have been possible without the work coming from Joe about trying to take, in this case, STM chip technology that is invariant. And there's a lot of signal processing, image processing that goes into this. So it's really a large team that is working on the actual knowledge there. It's led by Zyvex, but I think there are 5 or 6 universities participating in this. UIUC is one of them. UT Austin, UT Dallas. Trying to remember all the universities. Some of them will come back to me. And I should point out, when I talked about these, the previous one, this is also a multi institutional collaboration. It has UIUC as the lead, but also has NRL as one of the participants in the research lab. So another program of mine is the next Science and Technology Fundamentals program. And again, as part of the ABBA team, we have Professor Joe Rogers here. This is trying to look at optical devices. In this case, they're looking at plasmonic MEMS in order to use it to shape light and do things. And the focus areas that we're looking at, we're focusing on reliability. MEMS designs, it has been there for a long time, but they're not making it to marketplace because of reliability. And I'm happy to report Samsung now has cell phones that has MEMS switches. And these came out of the work that came out of one of our centers. And that's the one from UC San Diego. This is the reliability physics. They've solved that problem, and now Samsung now uses these MEMS switches. The next thing is to get them to much higher power levels so that I can use them instead of using them with receivers, or in this case cell phones. Can I use them with cell phone towers? And an interesting one is they use one led by UC Irvine. And it's again, it has John Hopkins, it has University of Maryland, it has Stanford University, it has UC Berkeley as part of that team. And they're focused on microfluidics. Essentially, they're trying to, I would say, one of the objectives is to create a foundry-like process for plastics and things that you use in microfluidics. And they've done, one of the drivers is to build something that will allow you to detect malaria in the field. And they come up with very clever approaches to do fine blood tests without much. And actually, in the previous incarnation of this, it had the project, one of the projects that's become a company in Boston. It had from Harvard. I won't spend all the time on this. So yes, a key component of the NETSMEMS is also a group led by Stanford University. And Stanford focuses on interfaces. The Stanford University focuses on interfacial engineering. How do we intervene? And a key component that is to understand what's really going on between materials. And if the atom probe tomography has played a really strong part in how interfaces evolve over time. And this team, again, is multidisciplinary. It has Stanford, it has UC, University of Washington in Seattle, it has Iowa State University, and UC Berkeley, all in that team. So we've talked about a little bit about NETSMEMS at the local level. Now let's look at the materials level, what is going on. There's Dr. Brian Holloway from DSO. He's looking into local control of material synthesis. And these are the programs that will be coming out soon also, so it's something to be on the lookout for. And the key insight in hand is that, well, if you look at all the stages that you need to deposit materials, from flux to the surface mobility, to reactivity, and you break them up, actually the optimal temperature may be different from one to the other. And then you tend to use the temperature, which is the limiting one. And so if we can play with that, will it be possible to drive down the temperature at which we deposit materials, but still keep the quality that we like to have and of the materials? So his goal is to take things that are about 1,000 degrees and drive them to 100 degrees. And the idea is to, in this case, use other sources of energy to control what's going on either in the reactivity or surface mobility, but make sure that the substrate that you're depositing on. A classic point, in case in point, would be for those of us who work on large area electronics, you cannot have good substrates that would. And then what happens is that if you deposit pentacene on any of these, if we raise the temperature to get it to be more crystalline, pentacene, sublimates, leaves the surface, so you have nothing growth. But if you can find some other means of giving energy for two pentacene molecules to move on the surface without raising the temperature, possibly I'll be able to go better materials. And so his main goal is to lower the temperature that we can use to put materials down. A program of mine is the Nano-Electromechanical Computers program. And it started a while ago. And the first stage, we just said, can we make switches? And as I alluded to earlier on, what was the problem we're trying to solve? Leakage current in your microsystems. It's always a problem. It drains battery power. And why am I interested? If I want to put sensors out in the field, I want them to last as long as possible. I don't want them to be using them on leakage, which does not do me any good. I want it to use on computation. And all I need to do is to only use energy when I do computation. Don't use energy when I don't need to do that. So the key thing we saw was that, okay, the leakage comes from the fact that you are using a semiconductor in the first place. But you can't get away from the performance you get from that because you have to shrink the gate length down. That's how you get performance. You are limited to your velocity you can get. So the only way to get performance is shrinking the gate length down. But if you shrink the gate length down, leakage current results. So can we use vacuum gaps or relay-like structures? And in that case, use to build computation along those lines. And two things we wanted to do. Can we use it to break the leakage path? So use it to gate, or use it to break the leakage path, or use it to do computation all by itself. And without going much into this, if you look at the latest spectrum, IEEE spectrum, there was an article that came out of UC Berkeley, CJK. Essentially, they built a microcontroller totally on using CMOS technology based on using relays. That came out in the IEEE spectrum of last month, or maybe earlier this month. Yeah, it came out in April. A program that's quite interesting from Tim Broderick is the Surface Enhanced Raman, in which there are a number of good approaches they're using, essentially all based around building optical couplers, antennas, optical antenna, and optical transformer, and use it to localize energy to where you have your signal that you want to detect, usually some biological or chemical. And in this case, the goal is to enhance the signal by a factor of 10 to the 12, which they've done. And actually, you can do standard detection these days. Okay. I'll move on quickly in these cases. We're about to come to stiction has always been a problem. And it's because you have gaps that are the nanoscale. And so the feeling is that Casimir effect has been one of those that we didn't understand and how to get to them. So we initiated programs. These are not device-based programs. They do build structures to try to understand what's going on. But we're trying to improve MEMS reliability and decrease addition. A key program that's also important is how to do thermal management. If you think of, when you try to remove heat, you try to remove it as close as possible to the source so that you don't have thermal resistance. And the higher your thermal resistance, the higher your gradient. And so what has happened is that if you want to be able to remove it cleverly and maybe increase we need to then decrease the thickness. So you see there's a correlation between your thermal resistance and thickness of a field. But what happens is that as the thickness goes up, you have a situation whereby there's less compliance. So things break because of different thermal expansion coefficients. So it becomes difficult. You can use things to do that. So what ideas are coming were things like using copper nanosprings. Yes, indium does better, or could do better, but copper has much higher thermal conductivity. So by using springs, you get rid of that compliance limit and using nanosprings. In this case, if you're using nanotech graphite and solder, again, at the nanoscale to do thermal management. And in this case, using multi-wall carbon nanotubes, and in this case, using CNTs directly to do that. For those who do electronics, graphene zinc has been used in this case to grow epitaxial graphene materials on silicon substrates, and in this case, make devices that perform at about 300 gigahertz, which is quite big. and then build circuits that actually, in this case, are building RF resistors with inductors. On the optical side, we can decrease sizes. We just showed the example of silicon nanostructures which become photoluminescence when you decrease the size of the structures. So there's a lot of opportunities for nano, but what you need to do is be able to couple it to the systems we are interested in. And notice, first thing, there are big challenges in trying to put a lot of these nano systems together and how to interrogate them. So that's a main challenge. Can we place them at the precise location where we want them? And so that creates opportunities in terms of, and it also helps us to improve device performance. And so we're not just interested in making them small, but we're interested in putting them together into arrays and to structures. And that's how to work with us. So we walk through the broad agency announcement. So if you go to the Power website, there are always broad agency announcement. My suggestion is talk to the PMs and don't just respond without talking to the program manager. At least know where they're coming from. And if they have a workshop, please go to that workshop. Or if they have an industry day, participate in that industry day. You're likely to get a better chance. And be willing to, well, Illinois does extremely well with teaming because you have huge teams that easily form, easily get. But also you can use siblings. We have what we call office-wide PAs that are open all the time. And you have an idea that you think you can use to show how quickly something can become. They're always looking for ideas where they can take to a big program. So you can use a seedling process. If you have a hot idea, send in a seedling proposal after talking to the PM, and it's usually about a year long. Size about 200 to 300K. It's sizable, and you can get a lot of things done. And so you can fund a lot of initial research that way, and that tends to become big programs. And I'm going to stop there. We send us, the faculty members, to become program managers. The Young Faculty Award is another way that you can get funding. And also, we just finished the Young Faculty Awards for this year. What surprised me is that we had a huge crop of, last year we had 40 awarded, and this year is going to be more like 55, so it's growing. It's a growing program. And we always walk through program managers. The best way is to get your ideas in, come in, and we work with you for the next 4 or 5 years. The only thing is that you have to be willing to do 4 years of public service, be a US citizen, and move to Washington, D.C. Maybe we can negotiate that. So I'm done.
Thank you very much for extremely we have some time for questions.
Yeah.
So I was curious about the MEMS switching. Could you speak more about how that works?
Okay, the MEMS switches. I didn't have time to go into the details of that because I wanted to show all the other things we have. We initially explored 3 sets of a number of ideas, which is how can you build switches? One thing that came out is that this gap between the switches had to be at the nanoscale. And so we had what we call horizontal switches that's moved laterally. And that's the Stanford approach. You have what we call vertical moving switches, and but they're horizontal. They are horizontal plates, but they move vertically. And also we have vertical plates that move vertically. The ones that have been most successful have been the horizontal or vertical movement. Why? It's because it's easier to define gaps using thin films. That's why it's zero circuit, and that's the one that was able to do. And so how does it work? Well, you have to balance compliance, the spring compliance with the movement of the gap, how much voltage you have across it. And that design process also has to take into account that we don't want to walk above 1 volt. So there's a number of other constraints that we put in. One, you don't want tunneling to occur. And so with all that put together, they then went from making a switch to building how fast. Then the other condition is that they have to work with 1 nanosecond. So it's 1 volt, 1 nanosecond. And then the next thing was that, can you build digital building blocks? Can you build, inverters? So after doing inverters, can they build digital building blocks like multipliers, adders, which they did. And then the next thing is, can you configure them? And they're doing now 8-bit peak processor, taking the peak processor and essentially using it as 8-bit. The only thing they did not put in, they didn't put a lot of memory. But in the process, they developed a lot of technology. So you have to think about what's a mechanical delay, what's an electrical delay. So it actually brings new possibilities. Can I make a single switch ring oscillator? And you can, because the mechanical delay is different from the electrical delay. And so the feedback. There are lots of different nanotechnology connections. I skipped the dialysis like therapeutics, which is a new program by Dr. Tim Broderick. And there are several ones, but I'll speak to 2. What Tim is addressing is that soldiers easily can run into sepsis after injury. And sometimes it's not easy to get rid of it. So what he's trying to do is that treat it like you're doing dialysis, like kidney dialysis. Take out the blood, separate them into different particles, have a feedback control system in there, and not only have a feedback control, after separating them, be able to separate the good cells from the bad cells, and making sure you don't clog things, because that needs a lot of, and do all these and be able to remove all pathogens in 24 hours. So it's high flow. And so it's an interesting, I will have spent a lot more time on that, but I wanted to give a survey of the activity. The second one I will give is Living Foundries by Dr. Alicia Jackson. Living Foundries takes the idea that if you look at most biological processes, you tend to use huge parts, huge, containers to do it. And sometimes what you really need are almost small quantities that you can. So what she's doing has been to use the microelectronic paradigm and use that, in this case, to use it to essentially build things and use it for biological, but also from non-biological. And in that case, in most cases, using biological precursors as much as she can. Even though she may be doing something inorganic, she's using biological precursors as a. So I think, but she's another person that is in the office. And there's the eVocal nanosensors, again by Dr. Tim Broderick. And that's an active program.
Can you speak briefly, I was intrigued with kind of the slide about the Casimir effect enhancement program. What exactly is the goal of that initiative?
Well, the Casimir effect, the conjecture is that a lot of what we have is fiction comes from Casimir effect. If we understand it, we'll get rid of one of the key reliability issues that we see for MEMS nets. But also, we're thinking if we understand it, can we make interesting devices from it? And so, as of now, the focus in can we understand what the forces are, and we measure them accurately, but we build structures in order to do, and then characterize the properties of the surfaces, look at effects of surface hard atoms. So there's a lot more basic work going on before we try to use it in devices. And the first application is get rid of stiction. After that, then we worry about. But it's good that now we have, MEMS switches in your cell phones. I don't think Samsung will put them out if those things are not reliable, because you sue them and get a lot of money out of them. Question?
What about radiation hardness of these switch-based?
Oh, that's a good one. Those things, the switches, the mechanical switches, we are actually testing them for radiation hardness. We've done some tests, and they do extremely well. And do we fully understand why? Because we need to look at those that are built with metals versus those that are built with semiconductors. But thus far, we've not been able to detect any difference between those two, except when you have oxides, which charge up. Some cases you have oxide. The reason sometimes you have to put oxide is to use them as spacers. So it now tells you how do we strategically place things. And then we've been able to do more complex devices, and I didn't have time to go into them. Complex devices, instead of a 3-terminal device, we build 4-terminal devices. Just like your MOSFET, you build a body, you can negate, and you can play between those two to control switching. Just like you use the body contact in a MOSFET to control what your threshold voltage is, you can use that to control your threshold voltage. And now we're going to 6-terminal devices. And actually it makes your logic a lot simpler, because in regular electronics, it's your electrical delay that matters the most. In nano-electrical systems, it's the mechanical delay. So your design approach would be that I build everything within one mechanical delay. Instead of trying to build things in several delays, the way you cascade gates and do things, you try to do a lot more parallel things within one mechanical delay.
Okay. Thank you very much.
For how long can you operate those switches? I mean, what is your reliability?
Well, there are two things. Are we talking about capacitive switches or ohmic switches? Those two, there's a big difference. The ones that made it into cell phones are capacitive switches. They don't go all the way. But there are ways that people have come up. It's a question of, when you brought up the question of, dielectrics, diamond is a good material in the sense that it's at the same time wide bandgap semiconductor, but you can also control its leakage. What you need is control leakage, and that has been level 2. In terms of the ohmic switches, we're doing a lot more fundamental work still on that, and we've been able to make them work. There are two things that control them. Temperature doesn't control reliability of the switches. Unlike most of your semiconductor, where you use temperature to do. The way to accelerate them is the field. And it's about how much energy you are putting on each time you make a contact. Because each time you go in, you're taking some mechanical energy and dissipating it. And so by minimizing that mechanical energy, you can prolong the life. So one way to do it is to decrease your gap, but make sure you don't have tunneling, but at the same time, make sure you don't have high voltage. And by reducing the voltage, you can prolong the life. There's a law that shows that this goes almost, not exponentially, but it's not far from linear with the voltage you're operating. So the lower the voltage you have, you can prolong the life to as long as you want. I think I can't give you a specific record. You know, we are working towards 10 to the 17 switches. That's the goal there. 10 to the 17 number of switches. That's the lifetime we're projecting. They've gone all the way to about 10 to the 15 switches. That's